Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We're continuing with our thermodynamic lectures. Today we want to look at the Reynolds Analogy, advance it a little bit further and see how finally we can end up tailoring it for use, especially in the ratio of heat transfer to the shear stress in tubes and under turbulent conditions. So just want to provide further modification. Reynolds Analogy. So if we recollect, Reynolds Analogy gave us the ratio of the rate of heat transfer to the shear stress. And the expression was as follows. For Q Cp Now, this quantity, we derived it in our lectures on Reynolds Analogy. And remember, we also saw Prandtl's Taylor modification of Reynolds Analogy. So I encourage you, humbly request you to just go through some of those lectures. It will help you advance in a more systematic way. Now, this was Reynolds Analogy, where we gave the ratio of the heat capacity, the ratio of the rate of heat transfer to the shear stress. Now, this expression, we said, can be used in analysis of flow along flat plates. So it can be used for analysis for flow on flat plate. Now when it comes to a smooth plate, when it comes to flow of a smooth plate, then we have to remember that the shear stress of a smooth plate, in the case of a smooth plate, case of flow, smooth plate, we have to realize that the shear stress, tau, is given by the friction factor over 2, where F is the friction factor, and this is a function of Reynolds number, and this is the density, and that's the velocity. And remember, F is a function of Reynolds number. So what is Reynolds number? What's Reynolds number? If you remember from our earlier lectures, the other lectures, we say that Reynolds number, Re, Reynolds number, Re, is rho mu Sx over mu. That's Reynolds number. Remember, mu is the dynamic viscosity. And remember, this dynamic viscosity also is in the expression for shear stress. So similarly, remember that tau, the shear stress, is also given by mu du dy equals to 0. We have that as expression, and that is the velocity gradient. Now, and that is the dynamic viscosity. And so, the other item which we need to, the other constant number which we need to know about is the Prandtl number. Prandtl number, which is simply, okay, very important for us to know. Because when you're dealing with fluids, those are the key quantities which will determine a lot of things. Now, if we rearrange the Reynolds expression, we say that tau omega, k omega over tau omega Cp was the S US. So if we rearrange this expression, which you call Reynolds Analogy, then we have Q omega over theta S is equals to tau omega Cp mu S. Now, through dimensional analysis, we want to develop expression which will give us what we call the Nusselt number. So through dimensional analysis, we want to obtain the Nusselt number, which is a very important quantity. Obtain the Nusselt. So we start by working on this quantity, which has been reorganized, that is Q over theta S is equals to tau omega Cp, tau over Cp US. So if we substitute, if we replace the tau, we now have Q theta S is equals to F rho squared S over 2. We've just replaced that with the expression tau Cp over US. Of course, these two terms will cancel, so that these two terms will cancel. We've just replaced, this is tau in place of that. So the two quantities will cancel, so we have rho US over 2 Cp. So if you multiply both sides by the dimensions length, it's over K, that is multiplying, place tau, and multiply by x over K. So when we do that, we have x over K, and x and K are terms which you're familiar with, their dimensions and thermal conductivity, dot Q omega W. Theta S will be F rho US over 2 x over K Cp. Rho US x over K Cp. Remember, we are trying to use dimensions, more of dimensional analysis, elimination, additions, to get an expression where we will have this particular important constants which I've mentioned, the Reynolds number, the Prandtl number, the Nusselt number appear. So, if we multiply by the dynamic viscosity, then we will have mu over K x Q omega over theta S will be equal to F over 2 not multiply, we want to divide. Dividing by. So we have x over mu k, that will be f over 2 rho mu s x divided by mu cp over k. And so as it is, we now have, this is an expression for Reynolds number. So we can put it in there. That's x over mu k, that's the dynamic viscosity, qw over theta s. Remember, theta is temperature, u is velocity. We derive those particular quantities in our lecture where we derive the Reynolds analogy expression. And that would be f over 2. The Reynolds number is now factored there, Cp over K. So if we remove this mu K by cross multiplying, so cross multiplying by mu, which is dynamic viscosity, what do we get? We get x over K qw over theta s is equals to f over 2 re mu cp over k. And now what is this other quantity? That is Prandtl's number. PR. So now we have gotten these fundamental quantities in fluid dynamics in the equation. So we now have, on simplification, now have x over k q omega theta s is equals to f over 2. Remember, f is friction factor and it's a function of Reynolds number, re PR. So, if we assume, for example, that the thermal boundary thickness and the velocity boundary thickness, if you remember, if we assume that our thermal boundary thickness and velocity boundary thickness, this is a familiar quantity which you know, we have free stream, this we have x, we have y. If we assume, remember this is these are not profiles which you're pretty familiar with. If we assume that PR is equals to 1.00 or sigma is equals to sigma t, then in that particular case, the equation will reduce to x over k q omega theta s q w over theta s will be f over 2 r e. That is very important for us to note, that x over k q w, so that this quantity here, we lump it, we call it Nusselt number at point x, that will be f over 2, and Reynolds number at x, where nu is the Nusselt number. Nu is the Nusselt number. Now, we notice very important quantities, that if, for example, suppose we wanted to adopt Reynolds Analogy expression to flow in a tube. We want to adopt Reynolds analogy expression flow in a tube. Remember, Reynolds expression, just recall, is Q, the ratio of the rate of heat transfer to the shear stress, that's the isobaric heat capacity. So was heat and velocity. So in the tube, if you look at those expressions which we used to derive the integrals, which we used to derive the Reynolds analogy, and I kindly again, once again, request you to go through those particular lectures so that we build the process systematically, because we cannot include all in a single lecture. They will be awfully long, and that will not be extremely nice in terms of keeping the concentration of people intact. So we have QW, tau W, remember W is the wall, Cp is equals to theta, that for temperature, and for the velocity. So in this derivation, the boundary was y is equals to sigma. But now in a tube, we don't have free stream. In a tube, we don't have free stream. So our y will correspond to the tube axis. In the tube, we have no free stream. Therefore, y will correspond to the tube axis. Just look at our lectures on flows in tubes and you'll see our configuration involving tubes. And therefore, the expression now becomes Q W theta R for U R. And since this expression is not a function, of y, so that means that the velocity profile and the temperature profile are kind of similar. They have geometric similarity. Not a function of y. Therefore, the velocity, thermal profiles have geometric similarity. And therefore we can simply use, once we take note of that, in that this quantity is not a function of y, then it means that they have a geometric similarity, that's the velocity and the thermal profiles. And so this expression is the expression which you'll use in a tube. But remember that we can actually go steps further and also work on the fact that they have geometrical similarity, so that this theta r u r can be assumed to be the same as the mean values of those particular quantities. And of course, remember from our earlier discussions on turbulent flows, we talked about means, we talked of the Reynolds decomposition, we had the expected value and we had the mean, and this actually cancelled out. But remember that in our expressions, we had, for example, for velocity, we had the mean velocity plus the velocity due to the turbulence, and we said that this quantity is the velocity as a result of those disruptions as a result of those velocity gradients, which resulted in turbulent flow. And so we talk to mean values. So the moment you see us being able to come up with the mean values, then it means that this expression here, Q, and of course U, we had two resolved in two components, plane. And so this Q, omega, tau omega, Cp, can be expressed as theta m, which is for temperature, and um, these are mean values, and this can be used for turbulent flows. Very good. And so, in summary, we just built up from the Reynolds analogy, where we have the rate of the heat transfer to that of the shear stress, built up with expressions so that we're able to work with smooth surfaces. We gave the expression for the plate surface. From it, we built using expressions for smooth surfaces, or smooth plate, as opposed to flat plate. And we are able to get expressions in terms of the shear expressions for shear stress. And in addition, we have built up the system so that we have the Nusselt number, which is expressed in terms as functions of the Reynolds number and the Prandtl number. And we know the assumptions which you made involving Prandtl number, where we say that the velocity, the thickness of the velocity boundary and that of the thermal boundary are the same. That means Prandtl number is 1, and we were able to come up with expressions, several expressions. And now we have just seen the assumptions that if we modify when you're in tubes, because you don't have free stream, then our Y will correspond to R, which is related to the tube axis. Just look at our lectures, the tube axis. And so we are able to get a Reynolds analogy expression for use in flowing tubes. And similarly, we have seen that because there is no functional relationship with the y-axis, so it means that basically the velocity profile and the thermal profiles are geometrically similar in a sense. And so we can use the mean values of the heat and this velocity, and that expression can be used in cases of turbulent flow. So thank you. Let's stop at that point. We'll continue our lectures.